Morning. Just a brief recap of the announcements. The quiz is a take-home quiz. I'll have to post that for those of you who are watching on video. It's quiz 7.2 is what it'll say. And the test has been moved from Friday to Monday. Now, for the homework that's due today, who thinks that they, do you mind, Nick, if I take a look at what you have for problem 2? Now, problem 2, part A, the question was, explain why you can treat the repeated selections as independent events. And this student wrote that since 500 voters are less than 1/10 of the population, we can treat it as if they're independent, which is correct. I hope that's what you wrote for part A. For part B, the question was, what's the probability that the first voter surveyed that did not vote for Mr. Trump is the third one surveyed? And technically what you want to do is state your model there. So the model, it's not just a matter of showing your arithmetic, like 0.78 squared times 0.22 is 0.5254. By the way, is that the answer you got for part B, 0.5254?
No.
1338.
Yeah, that's what I got.
Okay, so let's find out what setup would be good for that. If you did 0.1338, so the first voter that did not vote for Mr. Trump is the third one. So we're saying success is not voting for Trump. So that means the first voter did vote for Trump, the second one did vote for Trump, and the third one did not vote for Trump. Right? So oh, yeah. Okay, so did you set it up as 0.78 squared times 0.22?
Yeah.
0.7. Yeah.
Okay, so the question is, on a problem like this, how do you know whether to do 0.22 plus 0.78 times 0.22 plus 0.78 squared times 0.22? Oh, first of all, are you okay with using an x for multiplication?
Yeah.
I hope you're not okay with that. We don't want to use x's for multiplication anymore because they actually represent variables. So you can use a dot or parentheses. So how do we know that, what is it in the problem that tells us that this is not the correct setup? I mean, based on what we've been learning, you can certainly understand that someone might want to set it up like this. But how do we know that this is not the correct setup and that instead we only need this piece? Lewis.
Well, the question said it's asking for the probability of the third person or the first three people.
Yeah, it does say what's the probability that the first voter surveyed is the third one surveyed. If the first one who did not vote for Trump is the third one surveyed. If they had said, what's the probability that the first voter surveyed that did not vote for Mr. Trump is either the first or the second or the third one surveyed, then we would add them up. But they want to know just this case. So that's why for problem 2, letter B, the setup is this piece only. For part C, it says, what's the probability that the first voter surveyed that did not vote for Mr. Trump is found before the fifth one surveyed? That's when you would, before the fifth, so that's where you want to use something like, this would be like a GMS CDF if we wanted to do the whole thing. Now, friends, one thing I was going to say about part B is that it's not enough in part B to just write this down. If all you did for part B was write this down in your answer, then here's what you're missing. You're missing did you write the conditions for launch? Did you write a mini essay? And Andrew and Kennedy, I'm directing this question to everyone. In problem 2, part B, did you write a mini essay that summarized the conditions for launch, inspired by this word picture? Instead of jumping into the calculations of 0.78 squared times 0.22. Did you say, inspired by this picture, that, oh, by the way, there are two possible outcomes. Either voted for Trump or did not vote for Trump. The probability of a randomly selected voter voting for Trump is not constant. However, I pointed out part A, 10 times 500 is less than 11,000, so we can treat this sample, these events, as independent events. And, well, actually, basically what that means is, you might be wondering, well, what's the difference here? We can treat them as if the probability is constant, it's close enough, and the events are independent. So I can hear, as I just listen to myself talking, I'm hearing what you said in part A about when I asked for independent events. Did you hear what came up in conversation? What came up in conversation was the 10% rule. Said, well, yeah, they're independent because the 10% rule has been satisfied. We can treat them as if they are independent events. So there's no doubt some overlap between the 10% rule and independent events. So the question is, do they have to be separated out? And what we want you to do is treat the 10% condition separately from independent events. And the reason this causes us to reconsider what happened in part A, I want you to separate this out. I do not want you to say, oh, well, we satisfied the 10% condition, the green condition, therefore the blue condition is okay. No, what we want to do is say that the blue condition is satisfied because this is a representative sample produced at random. It's the fact that they said that it's a simple random sample that we can say that the independent or representative sample condition has been satisfied. So let's separate that out. Let's not mix the blue condition with the green condition. So that's a little nuance that I have to put in there. So yeah, talk about the conditions for launch and then say, oh, by the way, therefore the conditions have been satisfied to use the geometric model with a probability of success of 0.78. And then did you write a let statement? Let X represent the number of randomly selected voters until the, emphasize the word first pro-Trump voter is found. Add specific meaning to your variable. So that's something that you might have left off. And then once you do it once, you don't have to do it every time you use the model, but the first time you use a model, just like in the homework, the first time you use a model, articulate the conditions for launching this model and then describe your let statement. Yes, go ahead.
Why is it 0.78 instead of 0.22?
Oh yeah, so let's see what they're asking for. It's probably the first, well, it said that did not vote for Trump. You're right, since they're talking about not voting for Trump as being success, you're right. I had the wrong one. I had voting for Trump. We want to make it not voting for Trump. So, thank you, Justin. 0.22. All right. Now, in part D, it said find the mean and standard deviation for the number of voters in the sample that we would expect to have voted for Mr. Trump. And I gave you that formula right at the end of class yesterday. The mean of a random variable is going to be n times p. So I hope you took 500 times 0.78 to get your answer for part D. For the standard deviation of random variable x, I hope you took the square root of 500 times 0.78. times 0.22. By the way, those of you who type this into your calculator, what did the standard deviation come out to be? Yeah, so. No, it's no longer geometric, we're going to the binomial. Because in Part D, they're not talking about the first vote, they're talking about a fixed number of voters. So Part D switched over to the binomial model. The binomial model that, for the sample size, national public. So this binomial model has a mean of whatever 500 times 0.78 is, and a standard deviation of, who typed this in and can report to me what that number was? Is there a volunteer? Yeah, go ahead. 2628. That's voters, be the label on it. So that's where we're at so far in terms of that homework assignment. However, as promised, we are going to learn a little bit more today that will enable us to do Part E before you turn it in. Yes, go ahead.
I have to tell you why it's like a
Well, notice that in Part D, there's no mention of the word first. We're just concerned about a fixed number. How many? The number of voters. That's referring to fixed. Now, interestingly, we're going to work a lot more with the binomial model today. So I'm going to table any follow-up questions on that. And let's just take a look more in depth at the binomial model and the sorts of problems that we can solve using it. So I'm going to hand this out. While I'm handing this out, I'm going to have the camera paused, and then we'll pick up again when we're ready to go. One feature that you'll notice about class on Friday is that there will be a quiz called the word picture quiz, but that's a quiz to which you have the answers up front. You'll just need to practice. So, word picture quiz on Friday. Okay, we're ready to roll. We're on the handout entitled Probability Models Part 2 of 4. And would you also please take out your word picture quiz, because we're going to be filling in pieces of that as we go along. So, word picture quiz. Have that ready to go. For today's warm-up problem, we are taking a look at calculator syntax, which is a piece of the word picture quiz. In fact, you'll see in problem 5 of the word picture quiz has these 3, and I just want to see where you're at with this. See if you can fill in the parameters that are required for the NG and B rockets or models that we shoot off, and also what's required on the calculator. So how do you write them down, and then how do you type them into your calculator? Let's see where you're at in terms of remembering what the answers are to problem 5 on Friday's word picture quiz. Okay, well, it really is intended to be a short question. And here's what we're going to be looking for on Friday's word picture quiz. When you get to number 5, hopefully you'll remember that the normal model has a specified mean, mu, and standard deviation, sigma. Those are the 2 things you need to know to specify a particular bell curve. Now, how do you do normal CDF on the calculator? You need 2 z-scores, z sub L and z sub R. The z-score on the left of the shaded region and the z-score on the right of the shaded region. Geometric models need only 1 parameter. Does anyone recall what letter of the alphabet we use here? And it's P, probability of success. So think national public as you write N and P, because Geomet CDF requires, it requires don't think national public, think public radio. Think P for public, K sub R, radio, public radio, which is this last 2 words of the phrase national public radio. And then finally, the new model, the one we're going to spend a lot of time with today, is the binomial model. And here we use national public radio. When I say go, I'd like you to let the viewers at home hear the phrase out loud and in unison. National Public Radio. Ready, go.
National Public
Radio.
Thank you, young man. That was awesome. Okay, so Let's take a look at an example of the binomial model. It's the idea that Zoe was asking about, and we're really just at the beginnings of the stages of understanding that. What I want you to have out with you is the word picture that we started to put together yesterday, right at the end of class. The one that said in a binomial model there has to be two possible outcomes. The essay for flying this rocket has 4 sections. A red section talking about how there's 2 possible outcomes, maybe either vote for Trump or not vote for Trump. It's snowing or it's not snowing. The probability of P has to be constant, or if it's not constant, 10 little n is less than big N. And then on the side, write a sideways, you probably wrote this yesterday, independent or representative sample. And on the top, we've got not the word first, but the word fixed. If there's a fixed number of successes that we care about, we don't care about the first person who votes for Trump, we care about how many people in the sample have voted for Trump. What is the fixed number? We don't care what order they come in. You filled in yesterday that the formula for the mean of the binomial distribution, which by the way is a histogram that's going to look like a bell curve, it's going to be the number of people in the sample times the probability of success. You've already written down square root of NPQ. What you have not yet written down is the probability that the total number of people who are voting for Trump is equal to a particular number. So that's what we have to add to our word picture. So let's start to get familiar with what's going on here by considering the rocket or the model. I'm using rocket as a metaphor for model because some people have flown model rockets. B3, 0.1. Imagine that another polar vortex is expected to come through next week for the first 3 days. Like the polar vortex is going to be here for 3 days, and we expect that the probability of the administrator is sending out a message saying, no school, it's a cold day, for any one of those 3 days is 0.1. And imagine that those events are independent of each other. Like it might be, 10% chance of school being called off on Monday. On Tuesday, no matter what happened on Monday, there's a 10% chance of school being called off on Tuesday, same thing for Wednesday. In reality, if they call it off one day, then the chances are it's probably a lot higher chance that they'll call it off the next day. These polar vortexes tend to come in and live here for a while before they move on. But imagine that all 4 conditions of the binomial model have been satisfied. I mean, think about it. 2 possibilities, either school is called off or school is not called off. Imagine that the probability 0.1 is constant, that these are independent events, and we care about, we're looking at the fixed number of days. It's like, is it going to be 0 days of no school, 1, 2, or 3? We're focusing on probability questions like, what's the probability that 2 out of 3 days will be no school? Those are the sorts of questions we'll answer. The word first will not be in the question. So, tree diagrams are going to help you understand what's going on with binomial models. So let's set up a tree diagram for Monday, Tuesday, and Wednesday. So for Monday, we're going to have either C for canceled. School is going to be canceled or canceled complement. Complement means not. Not canceled means we have school. So the probability of school being canceled on Monday is 0.1. So what number must this be over here, class?
0.9.
Got to be 0.9. Okay, now let's go to Tuesday. On Tuesday, we're either going to have canceled or canceled complement. So 0.1, 0.9, 0.1, 0.9. And then the third layer of branches is going to be the Wednesday layer, which is either canceled or not canceled. So 2, 4, 6, 8, 8 leaves in this tree diagram. Okay, so 0.1, 0.9, 0.1, all these are 0.1, 0.9. Now, As we fill in the leaves, I'd like you not to go to your calculator, but instead to write sideways. You may want to turn your paper sideways. You might want to do this. You might want to write this leaf as sideways, 0.1 to the third times 0.9 to the 0. Now, 0.9 to the 0 is 1. So you might be wondering, why am I taking the time to write 0.9 to the 0 when it's just the number 1? Well, we're doing that for a reason, and that is to establish a larger pattern. This second leaf is going to be upper branch times middle branch times lower branch. So it's going to be, and for, I think for coloring purposes, we're going to start out black and then we'll highlight them. So the second leaf, we'll do the 0.1s first. It's upper branch, so we have 2 0.1s and a 0.9. So that's going to be 0.1 squared times 0.9 to the first. There's 2 days of no school and 1 day of school. Would you please fill in the other 6 branches, writing sideways, using both a 0.1 to the some number and then a 0.9 to some 0. I'm going to pause the camera and then we'll pick up when you've had a chance to finish that. So, young man, would you please tell me what you had for the third leaf and then just go ahead and read the other ones. I'll try to write as quickly as I can.
0.1 squared times 0.1 times 0.9 squared. 0.1 squared times 0.9. 0.1 times 0.9 squared. 0.1 times 0.9 squared. 0.1 to the 0 times 0.9 to the third.
Okay. Yeah, that's pretty good. Some of these I didn't even put parentheses around them. There's 3 types of leaves. These 8 leaves can be categorized into 3 types. There's the 1 day off, that's 4 types. There's either 0 days off of school, 1, 2, or 3. So I'm going to use, let's go to the highlighter, do red. I'm going to, if you have, we'll say 0 days of school, all 3 days off. There's only 1 of those. Okay? And then I'm going to switch over to yellow for the 1 day off. Notice the 1 day off it's like 0.9 to the first. There's, how many of those 1 day off of school leaves? I'm sorry, how many are there only 1 day of school? This is 0 days of school. How many of these leaves represent, there was 1 day of school?
3.
There's a total of 3 of those. So those get the yellow color. Now I'm going to go to green for the leaves that represent we have 2 days in school. And there's 3 of those. And then blue is the 3 days of school. It's school for 3 days. So 1, 3, 3, 1. That's a very important sequence of numbers. It happens to be row 3 of which triangle? Pascal's triangle. The binomial model leans heavily on Pascal's triangle. So we need to take a little bit of a detour here to make sure that you know what's going on with Pascal's triangle, because I want you to get to the point where you can write the model, which, by the way, yeah, here, let's bring this one to closure. I want to show you what this model is and why it is that you don't have to draw this really big tree diagram every time you want to use a binomial model. I want you to be able to skip the tree diagram and let's see what just happened here. Oh good, I can select. Sometimes it doesn't let me select. I have to shut down and restart the computer, which only takes about 10 minutes. Now, what I want you to do when you see B of 3, 0.01, I want to teach you today, that's like my main goal for class today, is to help you get to the point where you can write a table in which the top row is little x and the bottom row is the probability of capital X equals lowercase x, and the fixed number of school days is, actually, let's see, 0.1. Actually, x is going to represent, we have to define what x is. let capital X represent not the first day that we have no school, but the fixed is in really parentheses, is implied, but the number, the fixed number, I mean, I'm gonna write fixed in parentheses. We don't write it, but it's implied. The number of days off. X represents the number of days off school. That number of days off will be either 0 or 1 or 2 or 3. And friends, this is the big difference between a geometric model and a binomial model. Binomial models start out with 0, because it is possible to have 0 days off. But geometric models always start out with 1, because they're concerned about the first time that something actually happens. The first time something happens will never be on the 0th time. It doesn't make any sense. So that's one difference between these two models. And I'm going to actually make my table a little bit bigger so people can see it in the luxury and comfort of their own home. And then I'll shrink it down again. But without having to write out the tree diagram, I want you to get to the point where you can say 1, 3, 3, 1, which is row 3 of Pascal's triangle. So we have 1 red leaf, 3 yellow leaves, 3 green leaves, and 1 blue leaf. That's the first part of it. And then we've got 0.1 is value here. So we're going to go 0.1 to the third. And actually, no, we want 0.1 to the 0 first. I'll tell you why. The reason we want to write 0.1 to the 0 is because there's a 0 here. 1, 0.1 to the 0, 0.9 to the third. And every cell has 3 numbers. It has number of leaves, and then 0.1 to the something, 0.9 to the something, 0.1, 0.9, 0.1, 0.9. The exponents on 0.1 match the values of x. 0, 1, 2, 3. The exponents on q, see it's p to this number. P. The exponents on q, which is 1 minus p, descend 3, 2, 1, 0. That's the probability model. Now, you might be saying, well, there's a mismatch here. So to fix the mismatch, what I'm going to do is change that to red, this to blue, the yellows to green. It's just a symmetry issue. The yellows are green, and the greens I'm going to turn to yellow. The greens, I want those to be 0.1 squared. And the first 0.1 squared is here, there, and 0.1. That's another yellow. So now the color, did I just turn it back the way it was? 0.1 squared, I want it to be 0.1 to the first. I want it yellow. First. Okay, so, well, you get the idea. The table is symmetric. Gotta change this back. Okay, the ones that I want to be yellow are 0.1 to the first. So 0.1 to the first is yellow. Okay, so now the color coding matches up, but this is the easiest way to write it out. So, is that something you'd be able to do? Well, to be able to do that, you have to know the rows of Pascal's triangle. Here's Pascal's triangle. Row 0 of Pascal's triangle. Let's write the title here, Pascal's triangle. Row 0 is the number 1. Row 1 is 1, 1. Row 2 of Pascal's triangle is 1, 2, 1. So if we were looking at just Monday and Tuesday, 2 days, then the coefficients of the binomial model would be 1, 2, 1. Since we were looking at 3 days off, or 3 days, Monday, Tuesday, Wednesday, the coefficients are going to be 1, 3, 3, 1. If you want to find a row of Pascal's triangle, just take the previous row and understand that every row of Pascal's triangle begins with the number 1, and then to get the next number, you just add the 2 numbers above. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. So based on this, can someone tell me what is row 5 of Pascal's triangle? Raise your hand if you think you know. All right, Andrew, go ahead.
1, 5, 10, 10, 5, 1.
Way to go. Any questions on how to get row 5 of Pascal's triangle? Okay, then would all of you please find row 6 of Pascal's triangle? Go ahead and write it down. Row 6. When you're done, you can look up here, see if we agree. I hope you wrote 1, 6, 15, 20, 15, 6, and 1. Now, here's how we use Pascal's triangle to fill in a binomial model. In fact, here, let's take a look at 5 days of school. Suppose we're thinking, oh yeah, the polar vortex might be here for 5 whole days. Or we don't know if there's going to be a polar vortex or not, but we have this model. It's the model B of national public. So 5 days of school, suppose that 0.2 is the probability of school being called off on any given day. Can you draw, using row 5 of Pascal's triangle, the probability distribution for days 0, days off of school, 1, 2, 3, 4, or 5 days off of school? Using row 5 of Pascal's triangle, see if you can pull it off. I'm going to pause the camera, then we'll come back and see how you did. Fill in the probability distribution for the model B of 5, 0.2. Okay, we're back. Let's see how you did. If I'm doing this in real time, if I were you on Monday's test and the problem had to do with binomial 5, 0.2, here's how I would do it so that I'm not wasting my time. I would say, well, row 5 of Pascal's triangle is 1, 5, 10, 10, 5, 1. So I know that there's going to be 32 leaves on this tree. One of them will be in this category. 5 of the leaves will have to do with 1 day of no school. 10 of the 32 leaves will represent 2 days of no school, all the way up to only 1 of the 32 leaves of the tree diagram would have 5 days of no school. And then I would set up the double parentheses, although I saw on Lewis's paper the way he did it, he didn't even do parentheses, which a little bit faster, but I think for some reason when you're taking notes or when you're watching a teacher do this, it's a little easier to see these in parentheses. So I'm going to do 0.2, 0.8, just fill in all the 0.2, 0.8s all the way across. This is the easiest way to avoid making mental errors. And then for the exponents, start at 5, or no, start at 0. Go 0, 5, they have to add up to 5. 1, 4, 2, 3. This is actually a little risky because the math I'm doing in my head, it's a little less risky to go 0, 1, 2, 3, 4, 5, count up on the first set of parentheses, and then just count down. 5, 4, 3, 2, 1, 0. You now have the answers to all sorts of probability questions. Like, for example, if someone asked you, let's just put a little part A over here. What's the probability that, and suppose X represents the number of days off, that the number of days off is 4? What's the probability of having exactly 4 days of no school? The answer's right here in this box. It is 5 times 0.2 to the fourth times 0.8 to the first. And then on the calculator, we can actually get the same answer. By the way, what is the probability that the number of days of no school will be less than or equal to 3? 3 days of no school, 2 days, 1 day, or 0. Well, first of all, that means you would have to add up all of these numbers, 4 triplets of numbers, which to just type it in would be time consuming, but it's not bad using Binomial CDF. So let's learn how to use Binomial CDF using National Public Radio. On your calculator, take out your calculator. Let's find the probability of having 3 or fewer days off from school. So go to the distribution menu and press up arrow. There it has Geomet CDF, and up here, sure enough, Binomial CDF is for efficiently adding up numbers from this table. So Binomial CDF is, oops, what have I done? I wish I knew. So Binomial CDF, we're going to try it once again right there. Binomial CDF. So National Public Radio. N. National begins with N. N is for 5. 5 days of school. Public starts with P, which stands for the probability of success. And wait a second. How is X defined? Is X school or is X no school? We defined X as the number of days off. So suppose the question verbally is, suppose that the number of days off is less than or equal to 3. We'll take that same definition of X. Number of days off is less than or equal to 3. And the probability of having a day off, sure enough, we put it there first, so that's good. It's 0.2. Probability of a day off is 0.2. Kradio. Kradio is spelled K-R-A-D-I-O, where the K-R stands for K on the right. And what we're hoping to do is we're hoping to add up all the numbers in this region and this region has a left boundary and a right boundary. The left boundary is always going to be 0. The right boundary, the K value on the right, K sub R, Kradio, is 3. So if you want to add up all the numbers from 0, or all of these boxes, all of these probabilities from 0 to 3, then on your calculator, just type a 3. That's all you type in. But we need to type in both so that you have an idea of how powerful Binomial CDF is. That's typing in, that's getting the answer of 0.993. That's the answer to the question, what's the probability that there will be 3 or fewer days of no school? Pretty high. What if you had to type it in the long way? You would have to type in 1, please type this in with me, times 0.1 to the 0, times 0.8 to the 5th, plus, and now the second of 4 boxes, 5 times, did I really do 0.1? It's 0.2, 0.2 to the 0. So I typed in the first box, you type in the other 3 boxes, and we'll see if we get the same answer at 0.99328. That's a lot of work. This is the kind of work that motivates you to learn the Binomial CDF command. Now, I want to double check, because this is being taped and everything.
It's 10, not 1.
So I just want to make sure I typed in right. 1, so it goes 1, 5, 10, my 10s were not coming out. So I'm gonna have to insert a 0 here, insert 0. 10, 10. It's a good thing I checked. Insert 0. 1, 5, 10, 10. Those are the first four numbers of row 5 of Pascal's triangle. And it goes 0, 1, 2, 3 on the point 2s, and 5, 4, 3, 2. Here we go. Same answer. How many of you would prefer to type in binom CDF? It's like, binom CDF is the life for me. How many of you would prefer to just type in all 12 numbers? First triplet, second triplet, Andrew. Okay, thank you for sharing. Someone had their hand up. Does anyone have a question on this? Lewis, go ahead.
From the tree diagram, I could see YU times 0.2, 0.8, but why do you times 1, 5, 10, 10, 5?
Well, if I were to write out the tree diagram for a 5-day model, not just Monday, Tuesday, Wednesday, but Monday, Tuesday, Wednesday, Thursday, Friday, do you agree that there would be 32 leaves on that tree?
Okay, I understand.
There would be 32 leaves. Notice how the numbers in row 5 of Pascal's triangle add up to 32. 1 plus 5 is 6, plus 10 is 16, plus 10 is 26, plus 5 is 31, plus 1 is 32. So this tells us how many of each type of leaf we have. There's 6 types of leaves. There's the 0 days off leaves. There's 5 leaves for 1 day off. Monday, Tuesday, Wednesday, Thursday, Friday. There's 10 leaves for 2 days off, 10 leaves for 3, 5 for 4 days off, and only 1 leaf, one of the 32 leaves for 5 days off. Now, we have to go a little bit deeper into Pascal's triangle, because let's take, and you might have enough room on this, but let's take a look at Pascal's triangle from a perspective of combinations. So row 0 is 1, which is really 0, choose 0. If you have 0 days of school and you want to find out how many ways are there to have 0 days off, there's only one way, and that is to not call off school on the day that doesn't exist. Yeah, Andrew.
Just a quick question on the last problem. What if you had the probability of x is greater than or equal to 3? What would you do there?
Okay, so Andrew's asking just a super question. I mean, it's such a wonderful question. Would I term it heroic? No, let's not get carried away. But it's a really good question. And he said, what if it had been x is greater than or equal to 3? What if the question had been, what's the probability of having x is greater than or equal to 3 days off school? This will happen to you. The probability that x is greater than or equal to 3. So you've got your box. You're thinking 0, 1, 2, 3, 4, 5 are the options. And greater than or equal to 3 means this box, prefer to go yellow on that, shows it better. So, greater than or equal to 3. The way to get that, the way to add up the 3 yellow boxes is to take one minus the 3 green boxes. If you want 3 yellows, take 1 minus 3 greens. That's what's going on in your mind. What's going on paper is you take this and you write 1 minus the probability of x is less than or equal to 2. Okay? So that's 1 minus binom CDF of National Public Radio. Okay, so. In fact, let's take a peek at the word picture quiz. There's one like that on the word picture quiz. Does yours say, I change it for every quiz, and these are, the thing that's in handwriting on the quiz could change. But notice that here we have 400 days of school, probability of being called off is 0.25. What does it say on your paper right here?
X is less than or equal to 70.
Okay, x is less than or equal to 70. Practice using your binom CDF notation. Go ahead and write out, how would you type in the answer to that probability question? Is it gonna be a 1 minus deal or not a 1 minus deal? It's gonna be a not 1 minus deal because it's the left part of the probability distribution. I hope you wrote binom CDF of national 400, public 0.25, and all the way from 0 up to and including 70. And just to get an extra example out of this,
We have different numbers,
oh, I thought you had 70 here.
not like,
Where'd you get 400?
like.
Oh, you have different numbers there too, okay. On yours, you have 110.3. Okay, so let me change that on mine. So that it says 110.3. 110.3 is what it is on your paper. So your national public radio would be, national is in 110.3 and 70. Now, let's get a little extra practice on this. Would you please do a binom CDF for finding the probability that the value of the random variable is greater than 50? Try that one also. What's the probability that the value of the random variable is x greater than 50? I'm going to pause the camera and let you wrestle with that and find someone in your group who agrees. Well, friends, if you had to find the probability that x is greater than 50, that's from 51 on up. The first number that's greater than 50 is 51. So if you want to add all the numbers from 51 up to 110, you would take 1 minus the probability that x is less than or equal to 50. Okay? So that would be 1 minus binom CDF of National Public Radio, 110.350. Now, had there been a bar under here, had it been greater than or equal to 50, how would that have changed this number?
49.
Would have changed it to a 49. So notice how you've got to have some pretty good attention to detail. Are we all thumbs up for liking attention to detail? I like attention to detail. Okay? Alrighty, so that was all in response to Andrew's questions. Pretty good. Pretty good, Andrew. All right, so let's continue on. Where were we? Oh, you know, we can probably fill this in. Oh, yeah, some of you know what this means. It's not the fraction 12/6. It means 12 choose 6. Permutations and combinations. We need to learn about combinations, which are the skeleton of Pascal's triangle. That's how Pascal's triangle is built. It's using combinations. So we're right in the middle of doing this. And let's go to row 1. Think of row 1 in terms of soccer tryouts. Now, earlier I told you that row 1 of Pascal's triangle was 1, 1. But let's think of it in terms of combinations. The combinations look like fractions, but there's no fraction bar. It's a fraction without the bar. We have one person trying out for soccer. And you can either have 0 people selected, or there's one person trying out for the team and one person is selected. How many ways are there for one person to try out and for us to pick 0 of them? It's only one scenario. The person shows up, they work really hard, they're sweating, they're scoring lots of goals, and then we say, no, we don't want you on our team. They go home. There's only one way for that to happen. How many ways are there for there to be one person trying out and one person is selected? It's only one way. That's row 1 of Pascal's triangle. Row 2 of Pascal's triangle is 1, 2, 1, which is really 2 choose 0, 2 choose 1, 2 choose 2. 2 people show up, 0 of them are selected. That's only one. Wait for that to happen. Both of you go home. How many ways are there, how many outcomes are there for two people to try out, but only one is selected. Two, person A is selected or person B is selected. Two try out, two are accepted, only one way for that to happen. So, row 3 of Pascal's triangle 1, 3, 3, 1 is, in terms of combinations, 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. And you keep going like that. So, when we did row 5, for example, suppose you want to know what row 40 of Pascal's triangle is, and you don't want to have to take the time to write out rows 0 through 39, because so far the only way to get to row 40 is to base it off of row 39, right? But now, row 40 of Pascal's triangle can be written as 40 choose 0, 40 choose 1, all the way up to 40 choose 40. So these are, here's a way to specify the 41 numbers that are in row 40 of Pascal's triangle without having to write out rows 0 through 39. Well, how do I find out what 40 choose 0 is 1, and this is 40, but how do I find what 40 choose 2 is? Well, there's a formula that you're responsible for knowing, n choose r. If n people try out for the team and only r of them are selected, then the formula for finding that number in Pascal's triangle is n factorial over n minus r factorial times r factorial. Let's practice this a little bit. Let's take 7 choose 2. What is 7 choose 2? 7 choose 2 is going to be 7 factorial over 5 factorial, 2 factorial. Sometimes students get confused as to what 7 factorial means. Some people think that it means 7! No, what 7 factorial actually means is 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay? And 5 factorial means 5 times 4 times 3 times 2 times 1. And 2 factorial means 2 times 1. It's in yellow. We don't use yellow every day around here, but we're doing it today. So, notice how to find 7 choose 2. If 7 people try out for the team and only 2 of them are selected, or if there are 7 days of school and only 2 of them are no school days, how many different leaves would there be in that, let's do this up, in the 128 leaf tree diagram? There's 128 leaves because 2 to the 7th is 128. How many of those 128 leaves would be 2 days off of school leaves? Same thing as 7 people try out for the soccer team. How many different outcomes are there for 2 of them to be selected? Well, it's not nearly as scary as it looks, because 5 times 4 times 3 2 times 2 times 1 cancels out with that. It's just 42 divided by 2, 21. So that means that the third number in row 7 of Pascal's triangle, row 7 would be 1, 7, 21. That's the third number in row 7. You can just keep going. So, here, you try one. Practice evaluating a combination. What is 8 choose 3? Go ahead and try it. Use your formula to evaluate 8 choose 3, which, by the way, is sometimes written as 8C3, just an alternate representation. 8 people try out for the team. How many combinations of 3 distinct players are there? It's not permutations, it's not orders, it's combinations. Pausing the camera. And the camera's back on. What are the 3 factorials here that you would use? Does anyone know what they are? There's 1 up top, 2 down below. Frodo, go ahead. Yeah, 8 minus 3, and 3. Okay, now 8 factorial and 5 factorial cancel out, except for an 8 times 7 times 6 survives that cancellation. 3 factorial is just 3 times 2 times 1. And I know that 3 goes into 6 twice. 3 goes into 6 twice. So now the 2's cancel, it's 56. So it's doable by hand. But the calculator has an NCR command on it also. So you can get 56 on the calculator by doing this. 8 choose 3. Here we go. If your mode is classic, which honestly I hope it is, then just type in 8. and go to your probability menu, which is on math. So press 8, followed by math, and arrow to the probability submenu where you find the NCR command. 8 NCR3 is 56. Now, you do have the factorial command. Those of you who prefer to type in factorials, you can just type in 8 factorial by pressing 8 math probability 4, 8 factorial divided by parentheses, you got to group them together, 5 math probability 4 factorial times 3 factorial, which is just 3 times 2 times 1 or 6. But you're just going to practice using this sequence. You can get pretty fast at it. And except I just messed it up. So math, yeah, you can get really fast. Watch me. This should also give us 56. It does. So I think the fastest way to do that would be just using the NCR command. If you want to find the 4th number in row 8 of Pascal's triangle, just type 8 NCR 4 minus 1, or 8 NCR 3. Yeah, go ahead.
What is R again? Like, is that the amount of?
It's the value of K.
Isn't the desired amount?
It's actually, yeah, it's the value of K. So notice how, in fact, I'm glad you asked this because we have to fill it in. In general, and this is why I would recommend you write this down, if you got, let's put an X value here, probability of capital X equals X. Here's the binomial model for N, comma, P. The general binomial model starts out at 0. So we have N choose 0, P to the 0, Q to the N. The next number in the binomial distribution is N choose 1, P to the 1, Q to the N minus 1. The third number in the binomial distribution is N choose 2, P to the 2, Q to the N minus 2, dot, 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 and then the kth number. The kth probability in the binomial distribution is N choose K, P to the K times Q to the N minus K. So when Peter asked, what is R? R is actually K. It's like the kth number. Or it's the value K. It's the general number here. And this is what goes on the word picture. This is what you'll be quizzed on Friday. So let's go back to the word picture because now we can finally fill it in. The probability that capital X equals lowercase k is N choose K, P to the K, Q to the N minus K. So notice how that compares to the other P of X equals K. For the geometric model, it was Q to the K minus 1 times P. So both of them have a Q and a P. Both of them have a K. It's going to be a little challenging, but based on the work that we've done on filling in these big 2-layer rectangles of probability distributions, you'll probably think, oh yeah, okay, I see where they get this Q to the K minus 1 times B, because it's K minus 1 failures before the first success. And down here, every cell of a binomial probability distribution has a triplet of numbers. The first of the 3 numbers comes from row N of Pascal's triangle. The second number is always success to the whatever that number is, success to the K, and then failure to the N minus K, because both of the exponents have to add up to N. And it's true. K plus N minus K, they add up to N. So we have completed that picture, the binomial distribution. Hopefully you have number 5 filled in. Normal CDF is Z sub left comma Z sub right. CDF is public radio. Binomial CDF is national public radio. We're giving you, inverse normal. What numbers do you have filled in on this? What numbers are in the middle?
0.57.
Okay, so you got a 0.57. And you have shaded on the right?
Yeah.
Okay, what is the number shaded on the right?
0.16.
Okay, so you got a 0.16 shaded on the right. So if you wanted to find this number, you would take inverse normal of what number? If you wanted to know what Z sub R is, the inverse normal of what number? Oh, do you have, what number did you say you had filled in here? 0.5? 0.57. Okay. Which, by the way, since all three numbers have to add up to 1, 57, 67, 73, so this is 0.27 here by subtraction. Okay, who can tell me what number goes into inverse normal if you wanted to know how many standard deviations you are above the mean? Yeah, Lewis?
27 for ZL.
I want for ZR.
ZR will be 84.
Okay, 0.84 is correct. And for ZL, it's going to be 0.27. So, I think we've already filled this in. So what we've done here is I think we finally finished what problem 5 will look like on Friday's word picture quiz. Okay? I think I have a practice word picture quiz for you, so you can kind of rehearse it on your own. Let me pause the camera here. On your practice word picture quiz, which, by the way, I guess we didn't fill this one in. What numbers did you have on your note version for right here? 50 and 4? Okay, so if this were a word picture quiz, 50 and 4, then I would expect you to write 50 factorial over 46 factorial, 4 factorial equals 50 NCR 4. I want you to show me both ways to write 50 choose 4. The factorial version and the calculator version, both of which can be obtained on the calculator. You don't have to find out what the actual number is, because this is going to be a no calculator experience. So basically, you're just writing out the 2 ways that you can type that into the calculator. Okay, now, on your practice word picture quiz, please join me in picking different numbers so that you can practice with some different numbers. Let's delete these. So, on your practice one, cross off the numbers that are there, and let's use something different. Let's make this one 31 and 6. 31 choose 6. 31 people try out for the team. Only 6 are selected. How many ways can that happen? Or there's 31 days of school where there's a probability of calling the day off. In how many ways of the 2 to the 31st leaves, which is a lot of leaves? How many ways are there for 6 to be called off? Let's, I'm just going to close the door for a second. It's getting a little noisy. Okay, so you've got a Z sub L, Z sub R. Let's shade this area and make it a 0.11. Change that to 0.11 and change the middle to 0.40. Kind of small, but we'll go with that. Now, down here, instead of G of 0.15, let's make that G of 0.61. So change this to 0.61. And then find the TI-84 notation for the probability of random variable X is greater than 13. And then for the binomial model, please change those numbers to 36 N and 0.4. And change this question I think I just deleted that page. That's okay. Change that question to the probability of, I want to see what your previous one was. Probability of x, let's make it greater than or equal to. X is greater than or equal to, we have 36 possible, so it's greater than or equal to 30. Okay? So, that's that one, 2 of 4. Okay, so now you have a practice quiz to do. Let's go to our companion questions here, 2 of 4. The first companion question is color blindness. So please turn to problem 16. Let's jump right in. Alrighty. The color blindness example. About 8% of males are colorblind, and a researcher needs some double check here. Okay, so on average, if there's 8% males are colorblind, a researcher needs some colorblind subjects for an experiment, begins checking potential subjects. How many men should the researcher expect to check to find one who is colorblind? Now, that's kind of like a first success, so we're using G of 0.08, which is review. I want to skip the review problem and get to one that's actually binomial in nature. So let's skip to the problem let's take a look at what part B is asking. Part B says, what's the probability that she won't find anyone among the first 4? Okay. Yeah, that's a nice to know problem, but notice how, if you flip over to part C, they're still talking about the first and the first. And let's find a question that's binomial in nature. Problem 17 has a binomial in nature problem. So let's skip forward to number 17. Assume that 13% of people are left-handed, and if we select 5 people at random, so they're telling us n is equal to 5, find the probability of each outcome described below. Now, these are Bernoulli trials because there's 2 possible outcomes, left and not left-handed. The population of people is infinite, so this is not constant, but 5 people is less than 10% of all people. 7 billion people, 5 is not more than 10% of that. And since people are selected at random, so that's good. And that you already have filled in, or at least most of it filled in. The trials are considered independent of each other. So let's turn the page and take a look at what they're asking us here. Some of the questions are going to be geometric in nature, some are going to be binomial in nature. And the first one that's truly binomial in nature is part B, down here at the bottom. It says, what's the probability that there are some lefties? Some lefties means one or more lefties. Well, notice how this is broken down. Some lefties, that would be, how many lefties? That would be 1, 2, 3, 4, or 5. Instead of adding up all 5 of those cells, why don't we just take 1 minus the probability that there's 0 lefties? So from the probability distribution, you would be expected to fill out the numbers that are in this box. So you would be expected to go 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, 5 choose 5, and then go 0.13, 0.87 for each, 0.13, 0.87. And then fill in the exponents. The exponents on 0.13 go up. 0, 1, 2, 3, 4, and 5. The exponents on 0.87 go down, starting with 5. 5, 4, 3, 2, 1. Liftoff. Houston, we have a problem. So you're going to be expected to fill in those and then figure out, well, let's see, the probability of one or more lefties. Why do all of this, all of those yellow boxes, when we can just take 1 minus the red box? And you can see that's what they did here. Just take 1 minus the k equals 0 box. So what's the fastest way to type that into your calculator? I honestly think the fastest way to type it in is to just type in the number 1 minus 0.87 caret 5. Because 0.13 to the 0 is just 1. There's no point in typing that in. And 5 choose 0 is just 1. So on your calculator, practice typing in 1 minus 0.87 to the 5th. Because I think that's the fastest way to type it in. You don't always have to use binom CDF. You should be able to get the answer of 0.502 by doing just that. I'll give you that. Handout. Okay, now I've handed out the part 3 of 4 handout. And the problem I want you to look on there is tennis anyone, which is problem 25. So flip forward to problem 25, tennis anyone. A certain tennis player makes a successful first serve 70% of the time. Looks like they're talking P is 0.7. Assume that each serve is independent of the other. If she serves 6 times, so n is equal to 6, what's the probability that she gets? And then the first serves, yeah, all 6 of the serves are in. What's the probability of getting all 6 serves in? Now, we do have to do a little bit of work to justify launching the rocket. And the work that justifies the launch is, yeah, these can be considered Bernoulli trials because of all that. And since we have a fixed number of successes, we're going to use, don't write binom, just b of 6 comma 0.7 specifies the rocket. Okay, so if we define x as the fixed number of serves that are in, these are good serves, then what's the probability that she gets all 6 serves in? Well, that's the very last triplet. It's 6 choose 6, 0.7 to the 6, 0.3 to the 0. Which I will continually argue is best typed in using 0.7 caret 6. There's nothing more that has to be typed into your calculator, since 0.3 to the 0 is 1 and 6 choose 6 is 1. Now, what's the probability of getting exactly 4 serves in? Well, exactly 4 of the 7 cells in the probability distribution, we want the 6 choose 4 cell. So, I mean, 2 to the 6th is 64. There's 64 leaves on the tree diagram. 6 choose 4 of those leaves are 0.7 to the 4th times 0.3 squared. So how would you actually type that into your calculator? Here's where you would want to use NCR. The calculator notation here would be 6 NCR 4 times 0.7 to the 4th times 0.3 squared. So here's where, if this were on Monday's test, you would actually use, put a time sign here, you would use the NCR to type that in. That's the probability that exactly 4 of the serves are in. We don't care about the first serve being in, that would be geometric. What about at least 4 serves being in? What's that one gonna be about? Well, here is where you want the probability that x is 4 or x is 5 or x is 6. Notice that the binomial CDF notation would enable you to save a lot of time on that, 1 minus binomial CDF. Now, I would like you to do just the homework. All you gotta do is that practice quiz for homework. We will see you on Friday.